Hello and welcome to this quick introduction to SIMULIA Opera in marine applications. Typical marine applications for Opera include calculation and minimisation of naval signatures, cathodic protection, electric propulsion, and steering and power systems. Simulation is used alongside testing in order to cut costs and timescales early on in the design process. It aids the testing procedure by giving guidance on what to expect during testing, where to look in detail, and what range of output to cater for. It's also useful in terms of separating out effects that would only be available as a single value in testing. We'll start now with a quick look at some of Opera's capabilities before going on to marine applications. Opera's modeler can be used to generate complex parametric models from scratch or primitives. Alternatively, it can read and write many different formats of CAD file, both neutral formats and CAD specific. The geometry can be mixed. You can start in Opera, add a CAD model, then edit the merge models. Meshing is automated, but it does include facilities to finely control the mesh as required. Full nonlinear material modeling includes the option to model full hysteresis and magnetization curves during solution. Taking a look through the solution capabilities now, Opera started with a low-frequency electromagnetic solver. It's been used in many industries around the world to deliver accurate simulation results in computationally efficient timescales. It includes capabilities for ensuring high accuracy results from simplified methods, such as thin plate elements for ease of use of high aspect structures, such as magnetic shielding or ship's hulls. Besides electromagnetics, Opera 3D can solve thermal and stress problems to allow for full multi-physics solutions. Opera's post-processor offers the user all of the functionality necessary to make informed design decisions from interrogation of the results database. It offers, amongst other things, contours, graphs, vectors, patches, cut planes, and deformed shapes. The Opera Optimizer is a software tool which can assist users in achieving optimal designs. Optimization problems can be set in minutes, and the computer left to work out the best solution for one or multiple goals. That's a brief overview of Opera. Now we'll go on to look at marine applications and capabilities in more detail. The first marine application we'll look at is magnetic signatures. There are a number of contributions to a ship's magnetic signature. Interaction with the Earth's field leads to three effects: a static signature due to deflection of the Earth's magnetic field, and an eddy current signature due to movement within the Earth's field, and a permanent signature due to the remnant field in the structure. Onboard equipment such as generators, motors, and other electrical devices can produce stray fields which should be mitigated using shielding or bespoke design procedures for the device originally. Cathodic protection systems, if fitted, can also contribute to the vessel's signature. Magnetic flux density and field strength can be displayed anywhere in mesh volumes, so you can examine magnetic saturation in the steel and the field in individual compartments. The magnetic signature can be calculated anywhere in space. The field is computed from the integration of magnetization, so it can be calculated outside the mesh volume. Opera supports the computation of multiple moments, either for the entire vessel or individual components. The signature from the Earth's field can be opposed by onboard degaussing coils. These are added into the Opera simulation for the design process. Opera has a library of coils, for example, component parts like straight and curved, or preformed complete coils like racetrack and solenoids. They can be represented as a single filament for fast calculations. A naval vessel acquires a permanent signature over time due to magnetization from the Earth's field. This then requires de-perming, whereby the vessel is subjected to a reversing, gradually reducing magnetic field. To model de-perming, we use the hysteresis modeling, which uses interpolation from the major loop. The data is relatively easy to obtain, a simple table of B versus H in quadrants 1 through 3. Here you see a test cylinder being cycled through ever decreasing current amplitudes. The rocking motion of a vessel in the Earth's magnetic field induces eddy currents in conducting media. They produce a magnetic and electric signature. For this, you need to switch to the Opera Dynamic Solver. With it, you can solve AC or time-stepping problems. Typically, the most efficient way to model this is to leave the vessel stationary, then apply a moving magnetic field to simulate rocking. Remember to add other conducting materials to the static signature model, such as any aluminium superstructure. Here we see an optimization study. It's a simple example of a pressure hull with degaussing coils. The axial position of the coils can be varied. The total current that can be supplied is constrained. The black curve shows the best design for low integral and peak signature. The red curve has a lower integral signature but higher peaks. Cathodic protection simulation requires a model of the exterior surface of the vessel, including impressed current anodes, sacrificial anodes, and both painted and unprotected areas. The volume of the sea and seabed surrounding the vessel is meshed with finite elements and material conductivity is specified. We then solve Laplace's equation for current flow in the sea. After the analysis is run, we can display the potential distribution on the vessel, showing the effectiveness of the CP system. The electric field and current density distribution can be displayed anywhere in the modelled volume of sea and seabed. The resultant magnetic field from currents flowing in the sea and seabed can be calculated and displayed anywhere in space, not just in the meshed volume. Propulsion systems in the form of electric motors can be designed using Opera. The standard GUI and solvers provide all the tools you need to optimize the design of a particular type of motor, or the machine's environment can be used, which speeds up the typical motor design process. This can be used to design large electric motors for propulsion, generators for power systems, or systems such as anchor windlasses or pumps. The machine's environment is an easy-to-use template-driven development tool specifically designed for electrical machines engineers. It uses the full power of Opera to solve the models generated by the environment. It will assist with full multi-physics modeling and automate post-processing. It's integrated with the Opera Optimizer, allowing machines models to be rapidly optimized. Here are a selection of some of the analysis types that can be carried out automatically within the machine's environment. The environment handles pre-processing, solution, and post-processing. And similar to electrical machines, there's a transformer and reactor environment for speeding up the design of power systems. These may be carried on board, or any major power systems on the shore close to the dock may need to be assessed and shielded. So, in summary, Opera provides a fully functional system for simulating a selection of marine problems. Signatures, de-perming, cathodic protection, propulsion and power systems can be analysed with the same package. Advanced mashing facilities allow accurate calculation of fields using realistic sources. Advanced hysteretic material models enable de-perming simulation, and all this is industry proven and supported by experts. Thank you for joining us for this quick overview. Please don't hesitate to contact us for more information or check the Dassault Systems website.